Now we come to Chapter 8, which is about several different applications of integrals. We've spent a long time now learning how to do lots and lots of different kinds of hard integrals, and now we get to use them to solve other problems. We're going to focus on some geometric applications and then just briefly touch on a few other things. The first one we're going to talk about is arc length. That is, if there's some sort of curvy shape, curve, I guess. I was going to say curvy line, but that's sort of a contradiction. If you have a curve, how long is it? That is, if you exactly laid a string out along the curve and then stretched the string out straight, how long would the string be? And the problem is that we don't have a good way to measure distances that aren't in straight lines. Okay, so here's a little curve, and we want to ask how long that is, or in a more easily specified formulation, say we have the graph of a function, right? Y equals f of x is some sort of curve, and I want to know how long that curve is between x equals a and x equals b. That's the arc length of the graph between x equals a and x equals b. So how can we tell how long that is? Well, like most things in calculus, we start off by approximating it, and then make our approximation better and better and better and take a limit. So we did this with tangent lines. We found slopes of secant lines and then moved the 2 points closer and closer and closer together and took the limit, and that was the slope of a tangent line, the derivative. For areas, we approximated the area using a bunch of little rectangles and used more and more skinnier and skinnier rectangles, and that limit turned into the integral. So now we're going to do that with arc length. So if I want to approximate the length of the curve on the left, I can divide it up into a bunch of pieces by putting these dots on it, and then each pair of dots connect with a straight line segment. So I've got something made up of straight pieces that's pretty close to the original blue curve. Okay, so I approximate the curve with a lot of small line segments, and then the arc length of the curve is approximately equal to adding up all the lengths of those segments. That's the sum of the segment lengths. Well, if I used more segments, and they would therefore be smaller, I would get a better approximation. And if I used even more, I would get a better approximation. So I can end up getting the exact arc length by taking the sum of the segment lengths using n segments, and then letting that n go to infinity. So I use more and more and more segments. So it's the limit of the sum of the segment lengths as the number of segments approaches infinity. We'll do the same thing in the function graph setting, where we divide up that curve into a bunch of pieces using dots, and then connect each pair of dots using a straight line segment. And we add those up and use more and more and more line segments. Well, if I label the dots P0 on the far left, P1, P2, and then all the way up to the last dot on the far right being Pn, what I'm doing is adding up the segment length P0 to P1, and then P1 to P2, and P2 to P3, and so on. And each one of those is some horizontal or diagonal line segment, and it's easy to find the length of those line segments. So here's a close-up view of one of those line segments between the I minus first point and the ith point. And notice that each of those points is a point on the graph of the function, so it's got some x value, and then its y value is f of that x. Well, I know how to find the distance between those 2 points. I'll call it d. The length of that line segment, the distance, is the x distance, the horizontal distance squared, plus the y distance, which is the f of x distance squared, and then I take the square root. So that's from the Pythagorean theorem, or you can think of it as from the distance formula for graphs. So I have the square root of the change in x squared plus the change in f of x squared. And now I want to point out that the change in f over the change in x is approximately equal to the derivative, right? The derivative is the limit of change in f over change in x as change in x approaches 0. So that delta f of x is approximately equal to delta x times f prime of x. That means that the distance can be replaced with this expression when the delta x is small, so that f prime is approximately equal to change in f over change in x. So for small change in x's, for small line segments, that distance is the square root of the change in x squared times the quantity 1 plus f prime squared. And then I could factor the delta x squared out of the square root, bring it outside, and it would just be 1 delta x. So the length of all those line segments, you just add up a bunch of things that look like this. And then we take more and more of them and take the limit to get the exact arc length. As the number of segments goes to infinity, that means each individual segment gets shorter and shorter and shorter, but there's more and more of them. And so the delta x gets smaller and smaller and smaller and becomes a dx in the limit. And we're adding up a bunch of things, dx, and taking a limit. That's a Riemann sum, which means that the limit is going to turn into an integral. So this is an integral, but it's not the integral of the original function, it's the integral of this other expression. Okay, so this is the reason for the arc length formula. The arc length formula says if you've got a curve expressed in the equation y equals f of x from x equals a to x equals b, the length of that curve is this integral, the integral from a to b of the square root of 1 plus the derivative of f squared with respect to x. Okay. And that's great. That's all you need to know. Except sometimes you might want to express it differently for certain technical reasons. So now I'm going to talk about that. If you look at the thing that's being integrated, you could sort of bring that dx, so before we do that, if you look at the thing that's being integrated, f prime of x can be written in Leibniz notation as dy dx. So that's a different way to write that same thing. But you can sort of bring the dx into the square root, and then it would become a dx squared. And then if I multiply it through, the 1 times dx squared, and then that derivative times dx squared will just leave a dy squared. So it'll look like the square root of dx squared plus dy squared. That's not a way of writing it that leads to an integral that you can do easily, but it is a theoretically valid way of writing it. And it's useful because it lets us express this square root as something we'll call ds, which is the arc length differential. That is, it is a thing that represents a teeny tiny piece of arc length. So to get the total arc length, you integrate the teeny tiny pieces of arc length, ds. Okay. Well, that also means instead of factoring that dx squared out, I could have factored the dy squared out. So I can rearrange the ds to look like this. And in there, I have a dx over dy squared. That means the derivative of x with respect to y instead of the other way around, thinking of x as the function and y as the variable. So if we think of the equation as the equation x equals a function of y, right, so x is the function and y is the variable, from y equals c to y equals d, I can rewrite the arc length integral like this, the integral from c to d of the square root of 1 plus the derivative of that g function squared with respect to y. So we can write the arc length formula either as an integral in terms of x, dx, or as an integral in terms of y, dy, depending on the equation. One will be easier than the other usually, but they give the same answer. So for example, let's find the length of the part of the hyperbola xy equals 1, the part that's between the point 1, 1 and 2, 1/2. So the hyperbola looks like this, and then here's one little tiny piece of the hyperbola, and I want to know the length of that tiny piece. Okay. According to the first arc length formula we wrote down, I need to write an equation y equals some function of x. So I solve the equation xy equals 1 and get y equals 1 over x. I need to know the derivative of that, thinking of x as the variable, so that's negative 1 over x squared. And then the arc length is the integral from x values, 1 to 2, of the square root of 1 plus that derivative squared dx. Simplify slightly. And then I used Wolfram alpha to approximate this because it's not an easy integral to do. And it's about 1.132 units long. That's the length of that part of the curve. But I could have done it a different way. I could have, instead of solving to get y equals some function of x, I could have solved for x and got x equals the function 1 over y. Taken the derivative of that, thinking of y as the variable, and then The y version of the integral would be the integral between the y values. So y equals 1/2 up to y equals 1 of the function 1 plus this derivative squared with respect to y. Though it's not, it doesn't look like the same integral, it gives you the same value as its answer, 1.132 approximately. So either way will work. We'll look at some applications and some more examples in class. But to bring to class, I want you to set up an integral for the length of the curve y equals 3x from x equals 1 to x equals 4. You can set it up either way in terms of x or y. And, I mean, really you wouldn't need an integral to do this, right? Because y equals 3x is a straight line, but I want to see what the integral would look like if you did it that way. You don't need to actually do the integral, although it is an easy one, so you can if you want. I'll see you in class.